Why am I playing this song? Because I got my stylist back. It's working. Harmon stylist is back. All right. This is spring break like 1998. All right. All right. Time for me to start acting like a professor, I guess. I'm so excited, you guys. I emailed them. They sent me an update for my stylist, a software update. I'm happy. Okay. Let's continue on. So this will be the last lecture I record for Chapter 9. So we're just kind of doing a quick turnaround time, just hitting the highlights. So in this lecture, we're going to go over valence bond theory. And that's going to cover these last two learning goals 5 and learning goal 6. I'll remind you, I've canceled basically this last half of the chapter in the interest of time. Okay, so let's get into it. Valence bond theory, or VB theory, it is a theory rooted in quantum mechanics. So basically that means the orbitals. And it incorporates the assumption that covalent bonds formed when half-filled orbitals on different atoms. So half-filled orbitals on different atoms overlap or occur in the same region of space. Okay, so what that overlap means, right? So it's a term used in valence bond theory that describes that how bonds, chemical bonds, can arise when two atoms are literally overlapping in the same region of space. Okay? So for example, in this hydrogen, so if I have two hydrogens, right, and they're two half-filled orbitals, one s1 and one s1, okay? So as I move them closer and closer together, so when I move these two hydrogens, right, these are both, 1s1 hydrogens, both half-filled orbitals, right? And as they move closer and closer together, as they overlap, they form a bond, a single bond. We call that a sigma bond. Sigma, Greek letter for S, because it's really made from two s orbitals. So we can think of that as a single bond. I got my stylus back, but my handwriting still hasn't improved. So I want to show you a really cool simulation that I have on a program called Mathematica. We do this in my Chem 362 class, which is quantum mechanics for chemistry majors. If you are a chemistry major, you will have me eventually in physical chemistry, Chem 361, Chem 362. So this is a very cool program, all kinds of nasty math that you don't have to know. But what's really cool about this program, we've simulated two hydrogen atoms, and I can move them closer together. So this R2.5, that's 2.5 angstrom, which is 2.5 times 10 to the minus 10 meters apart. And what I can do in this really cool program is I can move them closer and closer together. And so you can see there's still two, 1s hydrogens, 1s1, and I'm getting them a little bit closer and closer, and it takes a minute to update. And now what maybe you can start to see is the shape is starting to get elongated. So the nuclei are becoming attracted to the electrons in the opposite molecules, okay? And so if I move them close enough, you can see that now they're starting to share overlap, and the hydrogen-hydrogen bond is observed to be about 1 angstrom. So there we go. Now I've, on my computer, made the H2 molecule with shared electron overlap that creates the sigma bond. Okay, so each of those dots represents each hydrogen nuclei. And all of this stuff around there, that's what we often refer to as the electron density. So this really would be kind of like what the molecule would look like if we could see it, at least we think, based on this idea of overlap, okay? So we call this process hybridization. So that's another term in valence bond theory, where this is the mixing or the overlap of atomic orbitals to generate, this should say a new set of orbitals that can then form covalent bonds, okay? So let's go through that. So we're gonna look at methane. I've got my, back to my Plato model of methane. But before I even make methane, let's talk about how we make what we call a hybridized carbon atom, okay? And so I'm gonna make it a tetrahedral hybridized carbon atom. So there's my carbon atom, right, with the 4 bonds in the tetrahedral arrangement. So what happens with this? Well, we know from carbon, right, here's my periodic table, 4 valence electrons, 1, 2, 3, 4. And that's gonna be 2s2, 2p2, as you can see right here, all right? So I'll call this is the atomic orbital configuration, or the electron configuration, right? Configuration, okay? And so this process of promotion happens. So one of these electrons gets promoted up to that level. And the important thing to note here is we have 4 unpaired electrons in carbon now, okay? And this is why we often see carbon form 4 bonds. Carbon makes this tetrahedral geometry really readily because of its atomic electron configuration. And so here, this process of hybridization, right, we just described, it's the mixing of these atomic orbitals, all right? And the new orbital that we say happens due to the tetrahedral arrangement is called an Sp3 orbital. So tetrahedral, oh my gosh, I can't spell. Tetrahedral, sure, something like that. We call it Sp3 because it's literally 1 s electron mixing with 3 p electrons, Sp3. That gives us this tetrahedral shape. And so what's really cool about this, I'm going to go to another simulation that that we've done in my physical chemistry class. So here we go, valence bond theory and plotting the hybrid orbitals is what we call these. So lots of nasty math here that you don't have to know yet. But when we solve these equations, so all of these equations, maybe you remember that little Greek letter psi, maybe you do, maybe you don't, from our chapter 7. We didn't talk about it too much, but that gives us the wave function. So all of these equations give us the wave function. So that's basically the mathematical solution to the atomic orbitals. And what's really cool is you notice here, this totally makes my tetrahedral shape. I mean, in this model, there's nothing in here, you have to trust me, there's nothing in here that tells me to make the bond angles 109.5. We can arrive to that result qualitatively by just recognizing that the geometry, to spread out these 4 electron pairs as much as possible, they adopt this tetrahedron shape. But what's really cool, when you solve the mathematical equations given by quantum mechanics, you get this tetrahedral shape, which is really neat. So if you're interested in this, we're going to do this in my Chem 362 class that for you chemistry majors, you'll take that class as a senior. Okay, so we get this Sp3 tetrahedral shape. And now, moving forward, I've got a half-filled orbital, so I've got 1 electron in each one of those Sp3. Remember, we've got 4 unpaired electrons in carbon, so there's 1, and there's 1, and there's 1, and there's one. And now in each of these hydrogens are each 1s1, so I'm drawing these arrows to represent electrons. So now, just like I showed you in that previous model, right, as I move these closer and closer together, they start to overlap and make a bond. And they make a bond because now in this shared overlap region, let me draw these arrows in the overlap region, okay? So now we actually get an electron pair in these overlapping regions, right? A spin up, spin down electron that makes these things bond, okay? Which is pretty cool. So this is where the tetrahedral shape comes from. Not only from predicting it just through simple geometry, trying to spread the atoms out evenly, but it also works with the hardcore quantum mechanics math. The math predicts it as well. So it's very, very cool, exciting stuff. Okay, so there's other ways that we can make Sp3. So I want you to recognize that Sp3 can really give us any tetrahedral geometry. So for example, if we look at nitrogen, so unhybridized nitrogen, that's the same thing as saying atomic nitrogen. We can see right here 5 valence electrons from the periodic table, 2s2, 2p3, okay? And so now when these things mix, what I'm going to have is 3 unpaired electrons and 1 paired electron, which is why we observe ammonia, NH3, to still have that tetrahedral geometry, except for, look, this empty stick, that represents this free electron pair, okay, which is pretty cool. So this pair right here becomes the lone pair, and now these empty 3 unpaired electrons can combine with 3 1s1 hydrogens. Let's go back to the red color, right, to give us that trigonal pyramidal shape. Remember, this is still tetrahedral, right? It still has the approximately 109.5, though we hopefully remember in ammonia, this angle is really 107 something, right, because of the lone pair. Okay, so what about water? Okay, so here we have atomic oxygen, which we know is 2s2, 2p4, right? 6 valence electrons, 2s2, 2p4. And so now when we hybridize these 4 orbitals, remember, once again, sp3 is mixing 1 s orbital with 3 p orbitals. So that makes us 4 possible geometries, 4 possible electron domains, okay? So now we can see that we've got 2 unpaired and 2 lone pairs, which is exactly what we observe in water, right? There's those 2 lone pairs, and here is my 2 hydrogens, okay? Pretty cool stuff. So they all adopt so let's draw in those electron pairs that make bonds. They all adopt the sp3 tetrahedral arrangement. However, because of their atomic electron configuration, this leads to the observation of the bent geometry, molecular geometry for water, the trigonal pyramidal for ammonia, and of course the tetrahedral molecular geometry for methane. Okay, moving along. So I'm going to get into the next type of hybridization, which is Sp2. Okay? And so as you might guess, Sp2 hybridization can occur when we mix 1s and only 2p's. Okay? And so Carbon can do this. Nitrogen can do this. There's a lot of atoms out there that can do Sp2 hybridization. And so what ends up happening in Sp2 hybridization, we only use, let's see, we promote. So the first thing that happens is, this is missing the slide for promotion, okay? So we promote this to make a 2s1, 2p3, all right? However, one p orbital gets left out of the mix, okay? So this is one extra atomic p orbital, okay? And so now what happens is, what we should recognize, all right, let's see if I can do this with my Plato models here, all right? So now you might notice, well, why is there 5 things sticking out of there? Well, what we get when we have these 3 Sp2 hybrid orbitals, okay, we should recognize that they are half filled, so there's only 1 electron in each of these Sp2 orbitals, like that. There they are, 1, 2, 3. However, if you remember the shape of p orbitals, right, they have this like 2 lobes, right? Well, we'll have some extra electron. You know, it'll be either in the top one or the bottom one. Doesn't really matter. It's arbitrary. Okay. And we also get the 120-degree bond angle from this. And I'll go to my simulation here. Okay. And here I solved the equations for, or really I'm making my students do it. This is the answer key though. And so what you get, you notice this shape for Sp2, the math predicts that it's 120 degrees. You have to take my word on it that this is 120 degrees. And the important part is that it's planar, right? Just like, let's see here. Now my Plato really does not hold up well. Okay, right? It's the trigonal planar, right? It is a plane, right? With 120-degree bond angles, okay? But now something really interesting can happen with these extra p orbitals, okay? And so what happens is we make a new type of bond, which is called a pi bond, or in other words, a double bond. So let's play with this molecule right here. This is called ethene, okay? And ethene is 2 carbons with a double-double bond, all right? And if you notice here, if you look at each carbon is an Sp2, or in other words, a trigonal planar arrangement. So it's 2 trigonal planars. So let's see if I can quickly build that with the Plato. Okay, so let's see. First, I'm just going to build the single bond. Oh man, the Plato is way too heavy for these toothpicks, right? So there are my 2 trigonal planars. I think my hands are getting in the way, right? Hopefully you can see that each one of those are trigonal planar, okay? But now, because if you look at this picture is getting crazy, right? So the overlap of the Sp2 bonds makes the sigma, okay? So I'll write sigma bond right here, okay? So that means one of these bonds is what we call a sigma bond. And then now what happens is, hopefully my Plato holds up. These 2 sticks that are sticking up, right? So there's my trigonal planars, okay? But now these 2 sticks that are sticking up, those are the 2 available p orbitals, right? Okay, and when they overlap, when they become close to each other, like it's showing here, right? So far away, maybe they're not bonded, but as you get these things closer together, something like this, okay, it forms the pi bond, okay? So in this doubly bonded molecule, one of those bonds is a pi bond, the other is a sigma bond. And what's important to note the sigma bond exists between the two nuclei. The sigma bond is what we call internuclear. The pi bond, I'll put another toothpick. The pi bond exists somewhere up here, okay? Off axis. So I'll say the sigma bond is internuclear. It's between the two nuclei. The pi bond is, I'll say, off axis, okay? And so let's see here. So before I go to this next example, I'll show you on my on this simulation, this other one, how I can make a pi bond. And so this one is just showing you, because it gets rather complicated, it's only showing you how we make the pi bond from two p orbitals, okay? So here's two p orbitals, and I've got them about 2.05 angstrom apart. And so this space between the two p orbitals, where it says the 0.0, that's where the nuclei would be, okay? So the internuclear zone exists between here. That's what would create the sigma bond. But now watch what happens if I get these things really close to each other, okay? Thinking, computing, there's the pi bond, right? And we don't know really, we can't say with certainty if it exists on top or bottom. So you can see my model calculates both. It predicts both. So this is not making, it's important to note, this is not a double bond. There's only going to be an electron pair in either the top one or the bottom one, okay? But all the same, the nuclei exist between this region. And so if this were a model of an actually double bonded molecule, we would just see a giant amount of electron density surrounding that internuclear zone, okay? And so that's actually what this picture shows right here. So let's look at the molecule formaldehyde. So that's this molecule right here. Formaldehyde, the stuff that you store critters, the jars that have the biological samples, bugs, and preserved things and the like, right? Formaldehyde. And if you notice the Lewis structure, right? The carbon, hydrogen, double bond, oxygen, that's making a trigonal planar, which I want you to recognize is Sp2. All right. And so now you can see what happens here on this picture. Let me go back to my red pen. We've got a sigma bond here between the carbon and hydrogen, right? Sigma bond. We've got another sigma bond here between this carbon and hydrogen, right? We've got another sigma bond between the carbon and oxygen, okay, that exists between the two nuclei. And then now you notice the pi bond, it can be either top or bottom. I'll just draw it up there. There's my pi bond. So 3 sigma bonds and 1 pi bond. And you also notice that if you look at oxygen here, the oxygen hybridization, it's also Sp2 hybridized. However, because it has these two pairs from the atomic configuration, this predicts the 2 lone pairs on oxygen. So this is all good. This really matches up with all of the theories nicely. Okay? So moving on. So let's talk about Sp hybridization. I want you to recognize Sp hybridization is synonymous with the geometry linear. Okay? And what happens in Sp hybridization, only one s orbital mixes with one p orbital. And then so what we're left with is 2 p orbitals. Or 2 electrons, 2 unhybridized p orbitals. And this is what will form a triple bond, which a triple bond we recognize is 1 sigma and 2 pi bonds. But this is where this gets a little tricky, okay? So what I have here, let's try to draw this, okay? Or not draw this rather, but let's make this molecule, okay? So the first thing I'm just going to show you are only my sigma bonds. And so, by the way, this molecule that I have right here, carbon triple bond with 2 hydrogens, this is what we call acetylene. And yes, that's the same acetylene. If any of you are machinists, or maybe you know people who are machinists, acetylene torch is what's often used in welding. So acetylene is quite flammable. So here would be my sigma bonds, right? All of the single bonds, okay? And now because there are 2 p orbitals, we have to remember that these are going to be like px, py, pz. So these 2 things sticking up right here make one of the p orbitals, which, you know, combining this toothpick and this toothpick makes the pi bond. However, and this gets really hard to see because my Play-Doh just doesn't want to hold up, that other pi bond is created at a 90-degree angle, right? You see that? So really, I've got now 2 off-axis bonds. I've got the internuclear sigma bond, which I'm pointing with my ring finger right there. I've got this pi bond that's on top, but now if I rotate it 90 degrees, right, that's what's going to make my 2 pi bonds. So really, I kind of like to describe this as a barrel. It's like a barrel of electron density surrounding the internuclear zone. And so hopefully this picture makes good sense, right? Here is a sigma bond from carbon to hydrogen. Here's a sigma bond from carbon to hydrogen. Here's another sigma bond from carbon to carbon. And now I'll have 1 pi bond that's above and 1 pi bond that's 90 degrees relative to the other one, okay? So there's a ton of electron density surrounding this carbon-carbon bond, all right? And that's why the bond is so short and strong. Remember, we talked about that in chapter 8, that triple bonds are very short and quite strong because there's all of this electron density surrounding those carbon-carbon nuclei. Okay? So moving forward. So we can get pretty complicated with this, even for simple molecules like CO2, all right? So with carbon dioxide, okay, this may be hard to recognize, but what I want you to see is each carbon, or the carbon, takes on an sp hybridization because it's linear. But if you look at each oxygen now, there's the double bond, that counts as one thing, you know, in my steric number, and 2 electron pairs. And so that means each of these oxygens are sp2, okay? And so I'm not even going to attempt to make this with my Play-Doh because I think it'll fall apart. But if you look at this model now, okay, what I have here is my carbon, my central carbon atom. The yellow represents the sigma bond, and I'll put electron pairs in there. So that represents the internuclear single bond, right? The bond that exists between the 2 nuclei. But now, and hopefully you can see this in this computer drawing. Because carbon is sp hybridized, it's got 2 open p orbitals. Remember, this lobe, the top and bottom, counts as 1 p orbital, and the lobe to the left and right count as 1 p orbital. And so now, one of these double bonds gets created up here, above this sigma bond. And then the other pi bond gets created out here, like coming out towards you. So it's kind of twisted, right? The electron geometry is twisted about the carbon atom. And that helps these electrons avoid each other as much as possible, right? The electrons want to spread around as much as they can. So CO2 is not like, you know, 2 double bonds on the same plane. It's 1 double bond above and 1 double bond out in front of you, 90 degrees, like that. Okay? Hopefully you can picture it. If not, find yourself some Play-Doh and toothpicks. Loads of fun. Okay, so let me look at our learning goals really quick. So in general, the main things that I'm concerned with are you knowing SP, SP2, SP3. However, I do want you to be somewhat familiar with the next two, Sp3D and Sp3D2. And I'm just going to go through both of these ones a little bit faster, and hopefully you can see the pattern. So Sp3D comes from mixing one s orbital, three p orbitals, and one d orbital. Okay? And so if we look at this for phosphorus, right, here's phosphorus, and this is why we started talking about things that can violate the octet rule. Well, hopefully this is, you can see why they're able to do that, because they can now hybridize with the D block. So they can spill over into the D block. And phosphorus, we recognize, is 3s2, 3p3. Okay? So when I promote one of those s electrons, that gives me 1, 2, 3, 4, 5 unpaired electrons, which means I can make 5 sigma bonds. All right, and here they are. 1, 2, 3, 4, 5. And I can get 5 bonds out of that, because now if I pair this phosphorus up with fluorine, for example, and remember fluorine as an atom looks like this, right? Fluorine's 7 valence electrons. It has 1 unpaired electron. So it is quite happy to pair up with that Sp3D hybridized phosphorus to give us 5 sigma bonds, which we call trigonal bipyramidal for the electron geometry. In this case, also the molecular geometry would be trigonal bipyramidal. But we recognize that if, let's say, if it weren't paired up with 5 fluorines, if let's suppose there were some lone pairs on phosphorus, it's still going to adopt, or excuse me, no, I take that back. Phosphorus, because it has the 5 unpaired, doesn't really want to create an extra electron pair. It wants to create 5 bonds. But if you look at sulfur, sulfur contains 1 extra, so that's why we can often see sulfur having electron pairs, like a lone pair on the sulfur atom, or we also see sulfur readily forming 6 bonds. And I think I have that next. Yes, the next one, SF6. So we recognize sulfur with 6 valence electrons, 1, 2, 3, 4, 5, 6, 3s2, 3p4. When all of these promote, you now have 1, 2, 3, 4, 5, 6 unpaired electrons, which we call Sp3D2. So 1s, 3 p's, and 2 d's to give me 6 bonds. It will make then what we call the octahedral geometry. Okay? So I want you to be a little bit more familiar with Sp, Sp2, and Sp3, because those make up almost everything that you'll encounter in the real world in chemistry. But certainly recognizing that the trend continues. If we want to make 5 bonds, Sp3D. If we want to make 6 bonds, Sp3D2. We could make 7 bonds with Sp3D3, although that becomes increasingly more rare. Okay? So great. So that really kind of wraps it up for this chapter. As you can kind of see, if I was on pace or if it was a different semester, there's a whole bunch more we would do with this. But I think that's going to really cover, especially what you need to know for those of you who go on to take organic chemistry. You'll learn about all this stuff in OChem, as well as Chem 110. We'll pick up a little bit more on this. So certainly if you're interested in reading the rest of Chapter 9, I would encourage that. But this is really just sections 9.2, 9.3, and 9.4. Okay, folks, I will see you on Friday.